Welcome to this webcast. I'm John Glossner, and I'm here to talk about the Heterogeneous System Architecture Foundation. I'll talk a little bit about the organization in general, and then focus on the heterogeneous programming problem and the solutions that we've come up with for these systems that have all different types of processors in them. Most of the time, though, we'll be talking about how do you program these and what are the results and the hardware that's available for running an HSA system. So let's start with the foundation itself. So it was founded in 2012 with the goal and the mission of developing a new platform for heterogeneous systems. Heterogeneous systems being multiple different types of processors, and then how could you program them in the same sense as like Java, you can run once, write once, run anywhere, and not have to worry about what type of CPU you're running on, ARM, MIPS, x86. Heterogeneous systems being the same thing, where now you have different mixes of processors in the same system. So how do you program a platform like that at a level of abstraction that's easy for a developer? So the first couple of years we set out to try to establish the hardware for that, and then the next couple to build the software infrastructure. And so that culminated in a version 1 specifications that were released in March of 2015. And then more recently, we've just started to have hardware become available that fully supports these specifications. So some of the members in the foundation include most of the semiconductor manufacturers, IP providers, tools providers, system software support from a wide range of different domains, including signal processing, including graphics, including CPUs, neural networks, and also with academic support. So there's a number of centers of competence, there's a number of universities that are making contributions in both research to HSA systems. But of the founders, ARM, AMD, Imagination, MediaTek, Qualcomm, and Samsung put together the overall structure, joined also by LG and Huaxia GPT. Established working groups, actively contribute to all of these working groups, and have generated a set of specifications that we'll look at. So first and foremost, HSA is an open architecture where anyone can join. There's a set of specifications, a programmer's reference manual, system architecture, and runtime. These are freely available. You can download them from the HSA Foundation's website. They're delivered royalty-free, unencumbered from IP, and are able then to abstract out the heterogeneous programming so that it's instruction set agnostic. So it doesn't matter whether you're a CPU, a GPU, a DSP, FPGA. It's completely agnostic, and a virtual instruction set is provided in the programmer's reference manual to support that. So HSA is intended to be run on all different types of devices, from small IoT devices with sensors that are just giving monitor analytics, all the way up to high-end compute servers that are running very sophisticated intelligence and analytics in the cloud. So it's specifically architected to support that wide range of devices and complex SoCs, and making them easy to program. So let's take a look at what is the problem. So we have pretty much everything built today is a heterogeneous system with multiple types of processors. They have huge amounts of compute capability available to them. Even it can be done on CPUs and clusters all the way to the accelerators, which are more typical. However, that programming, and none of those programming models are standardized. And when you have different numbers of cores and devices, it's hard to optimize and scale one generation to another. And currently, they're completely non-portable. So these are the systems that you have to put in place to be able to easily program these. So the goal of HSA is to bring together that compute app abstraction where you don't have to worry about the underlying processors in a heterogeneous system in a scalable, performance-minded way. So let's take a look first at the hardware. And I think it's been widely recognized that the HSA Foundation has really had a profound impact on hardware architecture, even Intel's. And the basic answer to that is cache-coherent shared virtual memory, the underlying mechanism that makes this work. But let's take a look at why. So if we go back to early legacy compute, here you would have, your desktop system, which had a number of usually x86 CPUs in it. It would have to talk across some bus, usually PCIe, to a GPU, which had a huge compute capability. But the thing is these were all in different memory systems. And so this memory couldn't easily talk to that memory. They weren't kept coherent. You had to copy data over into this memory. This tool chain for the GPU was completely different programming model and tool chain from this one for the CPU. And so there were a lot of proprietary tool chains, difficult to program, and pretty much you had to be an expert programmer to make this work. So let's skip ahead one more generation. It got a little bit better because these compute devices were at least integrated now on the same chip, but they still had completely separate memory spaces. So you still had these copies, although it was a little more efficient because they're still closer together, but still had multiple tool chains and everything else, just a little bit faster. What today's systems have that HSA has strongly influenced is unified, coherent shared virtual memory across all the processors. So that means the CPUs are generating addresses that map to a specific location. The GPU compute units are generating addresses in shared virtual memory that map to also the exact same physical address, and any other accelerator in that system or any other kernel agent in that system can also access the exact same physical memory. And they're exactly architected to cooperate in this manner, and so now all of those copies that used to go across that bus are now removed. So that's the basic hardware platform. So let's talk about how now you build software on top of that to optimize it. So first, let's go over a few terms. If we talk about a host, we basically mean a CPU. Probably think x86, ARM, MIPS, this kind of processor. It has a native instruction set, and what it knows how to do is to dispatch commands and specifically construct queues that other kernel agents will know how to execute from. So what do we mean by a kernel agent? So these are the things that are the compute. So it's your GPU, your image signal processor, your digital signal processor, and that is any agent that knows how to execute HSAL. HSAL being the HSA intermediate language, the virtual instruction set analogous to the Java virtual machine for Java programmers. It knows how to take these queues that were constructed by the CPU, pull out those pieces of HSAL, and execute them. If it has more work to do, once those queues are constructed, it also knows how to dispatch to itself into that same queue, which allows things like recursive programming and things like that. There is a concept of any other agent, and this is anything that knows the HSA memory model, which is cache-coherent shared virtual memory. So it doesn't execute HSAL, but it can still sit as an accelerator and avoid all of those copies that would traditionally have been required. Now, I left one line up here intentionally. So a host CPU can also act as a kernel compute agent. So the main difference, so this knows how to construct queues, and it has access to native CPU instruction set support. It can also execute HSAL itself. Kernel agents execute HSAL and know how to read and dispatch stuff into those packets. And then, of course, as I mentioned, anything else that knows the memory model is just another agent in the system. Okay, so now let's look at how you put one of these together from a software architecture point of view. So the applications programmer sits up here programming in whatever favorite language they like, OpenCL, C++. Those have always had their own runtime, which is fine. So that is still the same. So to here at this boundary, writing these programs looks exactly the same as it always has for the application developer. The runtime, however, now has to make a little bit of an enhancement to be able to speak to an HSA runtime, which is freely available, open. There's an open source implementation of a runtime on the website. And then the kernel agents talk through this HSA runtime. And the nice thing is you can have these for different vendors sitting in the same SoC. Okay, and these can be distributed either selectively or to all of them as the programming runtime chooses. So these kernel agents then take that HSA, HSAL, and finalize it and run it on their own native instruction set. So here you have one instruction set, here you have a different one for as many of those as exist in a system. So it looks the same to the programmer, and then the infrastructure supports this transparent application to the HSA runtime for the performance improvement of those kernels. So what is the benefit? So you get some benefits from our programming model. First, you have single source. And I don't mean that you have a string of a second program that gets read into the original source file and then somehow compiled somewhere else. It's the same programming language. The host and the agent are written in the same language, and there is no the debuggers and everything else and the autocompletes will all work, and so it's not just one of them is a string and the other is the real program. They sit in a single unified coherent address space, which means you can share pointers. So a pointer is a pointer. So a pointer on the host is the same as a pointer in an agent, a kernel agent, and so those can be passed rather than copying all that data. Parallelism is expressed exactly as it was before. So OpenMP is a source language, OpenCL is another one. When C++ 17 gets here, we'll have parallel STL that should be able to be automatically parallelized as well. We generate then HSAL. So from whatever language you pick, you'll generate HSAL, which is an intermediate representation. Think of it like a compiler intermediate representation. And that is what allows us to port these programs across all different types of processors. We provide then that runtime, which we showed, which is user level. So it's a thin user level API that allows for dispatching all of that. So the types of things you see, initialize a processor, send it some kind of signal, give it whatever agent information you're asking for, synchronization, the queues that I talked about, and memory management. So exactly the kind of stuff you would expect in a runtime. And then that runtime will speak to the programming language runtimes. So the memory model is compatible with C++, Java, .NET. It defines the ordering between all the threads. It's a relaxed consistency model, which is nice to have for parallel compute. There are also forward guarantee guidelines for making forward progress among all of those sets of threads. Visibility is controlled with load acquire, store release, and fences. Okay, so let's step back a minute and think about the motivation for why all of that hardware and software was designed. So before HSA, if you had an application that wanted to run on some agent, be it, let's say, a GPU over here. So you have your CPU, x86, let's say, that's running an application, and it wants to offload something to a GPU. So without these features, you would have to transfer your buffer over to the GPU, as we discussed. But it's not that simple, because the operating system is going to have to get involved to be able to do that. Once you tell the operating system you want a copy map, then the application is going to come back and actually queue that job, which again is going to require a scheduling inside of the operating system. Generally, these are running in kernel mode, so they're really not very efficient. So finally, that's going to go start a job then on the GPU. When it finishes, it's going to have to return to the operating system and say, okay, I'm done. So now the operating system can go schedule the application, which will say, okay, now I need you to go get me the buffer that just completed, and the operating system's going to copy it back, and finally, we're going to arrive and be done. Okay, so that's an awful lot of kernel level calls, an awful lot of overhead, just simply for an application to be able to start a job on a GPU. So now we're going to look piece by piece at how each of the things that have been architected get rid of much of this overhead. So first, let's say we're going to add shared virtual memory. So as soon as we do that, a pointer is a pointer, and therefore there's no reason to copy things any longer. Now if we look at cache coherency, well, okay, we don't have to copy them, but what cache coherency means is when I change a value of memory on my GPU, that's immediately reflected into the CPU or any other agent's cache that's executing within that same address space. Once you have cache coherency, so that happens in hardware, now you no longer have to do those transfers because you know immediately that the memory is updated as it's being changed. Okay, so that's the hardware side of things, but now we're going to add a couple of other software infrastructure on top of that to try to do even a little bit better. So we have a concept of signals, and so this is pretty much an asynchronous event that any two agents can send to each other without requiring the operating system to get involved. So it runs at user level, which is why it has to be architected. And you don't have to keep an agent up and querying this, polling for it. So there is an architected way you can put your agent to sleep, and when that signal happens, the system will wake it up. So you can wait on that, it can have conditions on it, and so it's basically a fast way at the user level for two agents to tell each other some event has happened. So once we add those signals, there's now no longer any reason that you have to request an operating system to schedule an application. The agent will directly communicate via a signal to the application that the job is finished. Okay, a little bit better. We still got a couple more to get rid of here. So HSA has a queuing model, which also is at user level and why it's architected. It again requires no operating system or driver support, and as we talked about, it dispatches little pieces of HSAL to any agent. So these queues sit there and are able to provide a schedule for all of the different agents. And so you can dispatch programs and agents and pieces of HSAL to any other agent automatically at user level. And that allows things, like tree traversal, or recursion, recursive language, recursive programming to be used. At the bottom of this, it requires cache coherent shared virtual memory, and then this is built as a layer on top of it, and it's available as a standard API that you can download from the website. Okay, so now that we have that, there's no reason any longer to schedule a job. So the operating system does not need to get involved at all. So let's step back and now see what happens when you have shared virtual memory, cache coherency, signals, and user mode queues. So now the application wants to queue a job. It can do so directly on to the GPU. When the GPU finishes the job, it can signal back immediately to the application. And all of that existing overhead that was going on in the operating system is now gone. So the way that dispatch works is you can have any number of applications written in any number of languages that all know how to write to a queue. So these are little pieces of program here, HSAL, that sit in these queues. A hardware agent, a kernel agent, a GPU, let's say, knows how to read these queues because it's architected, knows the order in which they want to read those queues, and then eats all of that HSAL inside and computes it, and then signals back to the application when it's been done. So that's the overall flow of a typical program inside of HSA. So let's look at what's in that virtual instruction set, the bytecode, so to speak, for heterogeneous systems. So first, let's step back and talk about portability. So if you think about CPUs, they've typically at least been backwards compatible. So when, AMD or Intel bring out a new version of an architecture, it will run binaries of all the previous versions. Same with ARM and MIPS. So that's for CPUs. For things like GPUs and DSPs, there's pretty much no backwards compatibility. And even within, like let's say a DSP architecture, even within the same generation of DSP, there's often no backward compatibility because the pipelines change, they were visible, and on and on. So trying to get CPUs as backward compatible is hard enough. Trying to get any particular kernel agent as backward compatible is almost impossible. Trying to put both of these in the same system that can run the same code is a huge challenge. So before I talk about exactly the bytecodes, let's also talk about the parallel execution model. So what the programmer sees is a three-dimensional grid in X, Y, and Z that's blocked out into sets of work groups where each item in a work group has a work item, which is the singular kind of compute that happens inside of that for multiple pieces, and then a wavefront is effectively how many of those can execute simultaneously. All of these boil down to nothing more than a number, an index that allows you to know where you are in that grid. So there's a unique coordinate for each of these, and then the programmer can specify certain parameters on how large a work group can be, how large a wavefront can be, etc. So that's the programming model. And then that virtual instruction set is going to take those parallel constructs, which can be specified in the programming language source, OpenMP in this case, and will compile it to this virtual instruction set. So you take your OpenMP or C++ code, you compile that to HSAL, and in particular the binary representation of HSAL, maintaining that explicitly parallel information. And then at runtime, you'll run a finalizer, which for any particular agent will take the binary representation of HSAL and compile it to the component's instruction set directly. So that removes the need to know anything specific about any particular instruction set, whether it's a CPU, a GPU, a DSP, or whatever. That complexity is in some case pushed to this finalizer, which takes the HSAL and then maps it to its own instruction set. It's explicitly parallel, so let's take a look at that. So there's about 135 opcodes in base HSAL. It looks like a RISC machine. It's register to register and load store. It supports IEEE floating point, including the 16-bit type. It also has integer, and particularly it also has fixed point, saturating arithmetic. Within that, it also has packed types. So it has a concept of SIMD both in the registers themselves and, as we'll see, in the parallel execution model. It has branches and functions and atomic operations, exceptions, and it assumes everything sits in shared virtual memory. For additional parallelism, it also has that same concept of a wavefront built into HSAL, and those can also be thought of as SIMD lanes, and with various flags you can make them active. They don't all have to participate. So using that, you end up with an instruction set syntax that looks pretty much like any other instruction set syntax, with the types, so loading from a global memory segment, an unsigned 64, and adding unsigned 64, etc. So I've just mentioned the global address space, but in fact there's 7 types of memory which are used for various purposes. But for the most part, as a programmer, you'll want the global segment because that's that memory that's visible to every HSA agent, so including CPUs and GPUs, coherent shared virtual memory. But there's also a concept that a group segment, so group memory, can also be thought of. So you have this work group over here, and so all of that memory is visible only to this work group and not to this one, let's say down here. So you can segment out that way. That allows you to optimize certain programs a little bit differently, in some cases better. And then synchronization can be provided for that memory with that group visibility. There's also a read-only segment, so if you have a number of constants that you know don't change, you can optimize by calling it read-only, and then so you can have multiple atomic reads going on and things like that. Most of the rest of the stuff is used by the finalizer, but there are concepts of private memory, spill places, and stuff only the kernel can use and things like that. So registers, as I mentioned, in 32-bit, there's 2K of them. So most likely you'll do a little bit of register allocation, but not a lot when you finalize this. 64-bit has 1K, and so on. So you can see that while these don't alias each other, there is a limit to the total number of registers that you can ever expect to find in an HSAL program. So that's specified, and so you can make some hardware assumptions about that as you are designing your SOCs. Okay, so that's sort of the infrastructure. So we saw the programming runtime and how you get the things to talk to each other. You saw it get converted to HSAL for any processor, doesn't matter which one it is. Basic functionality is executing HSAL. So now let's talk about how you program these things. So all of that is infrastructure. It's a lot of work, single source and all of that. But for the vast majority of developers, they're going to be more interested in what do I do to program this kind of system. And so the good news is you can use anything that you like. You can stay in your own preferred language. And in many of these cases, there's going to be a lot of open source tools available to support you. So if you like OpenCL, both AMD and Tampere University of Technology have open source, completely available tools that will compile OpenCL down to HSAL. If you like GCC, my company, General Processor Technologies, in conjunction with Parments from Tampere, Finland, sponsored GCC Brig, which takes HSAL in its binary form and translates it to GCC's tree intermediate form, which then allows you to optimize for vector and SIMD operations in GCC, and to finalize using GCC if you prefer. So the good part about that is if you're have a wide kind of architecture, some of these optimizations are more advantageous in VLIW-like devices. There is a C++ compiler that's fully open sourced and available, the Heterogeneous Compute Compiler, and that from a single C or C++ file will generate HSAL and x86 code for a combined system. So it also has built in already parallel STL and parallel for each and lambda expressions. Completely available to download and to use, and it separates out those kernel and host code regions. If you have a lot of code existing already in CUDA, there is a tool that will port your CUDA code to this same C++ code that I just talked about. And so in 98% of the cases, there's no intervention required. In some small percent of cases, you may have to fix up a few of the header calls. So the way it maps from HIP, what they call the tool, what AMD calls the tool, to CUDA, occasionally you'll need to fix that up a little bit. But in many cases, you can just literally put CUDA code through and it'll come out working into HSAL. So where is this all going? So there are the implementation from AMD and C++, and over C++11 and C++14, we've gotten more and more parallelism from threading and things like that. In C++17, we're going to get things like parallel STL. And in this case, we're very optimistic that we will be able to automatically partition compute and host code under the covers automatically for the programmer without them having to worry about it. That's already been accepted into C++17, so that will happen. SIMD parallelism we could also make use of, but that's not guaranteed to be implemented in the C++17, but let's wait and see. If it is, we'll be able to generate HSAL, which has that register-based SIMD as well, automatically from this type of code. If you like Python, Continuum Analytics provided Numba. It's a NumPy-aware Python compiler. It's completely open source as well and available on GitHub, and it has direct HSA support. So pretty much all you have to do is go in with a single line and say, hey, I want this thing to execute on a device, and it's an HSA device, so I target HSA. And then this is not some special library that sits underneath that replaces it with HSA already code. This compiler will take any universal function and automatically parallelize it. So all you have to let it know is that, yes, there is an HSA target in the system. And once you do that, then all of these universal functions, which is just standard Python, it's not library called, will be able to be automatically parallelized. Okay, so that's the programming aspect side of it. So keep using the same languages that you've always used, and we'll keep making more and more progress towards you not even having to enter a single additional line to specify parallelism. So that's all great. So the question is, for all of this abstraction, not having to worry about instruction sets any longer, what happens to performance? Might you expect that it gets worse? You probably wouldn't expect that you would get great acceleration, except for the inherent parallelism on the platform, if we can figure out how to take advantage of it. So let's start with Python. So Continuum ran code that computed the distance from a target to a whole set of points. And so, as I mentioned, this is auto-parallelized by the Numba compiler. And here, as the number of points continues to grow up into the million, again, with literally doing nothing, it automatically gets distributed and parallelized. So an 8x performance improvement at 1 million points with nothing, zero HSA knowledge required of any Python developer to achieve that. Okay, so Continuum has a webinar on that and walks through exactly what they did along with some other examples. Encourage you to go see it on GitHub. So Northeastern recently developed a set of heterogeneous benchmarks and published a paper on this. I've taken two examples from that paper. One is an FIR, which was memory intensive, and another is AES, which is compute intensive. And then they set the benchmark to be OpenCL 1.2 directly compiled to the GPU. And then they compare it against OpenCL 2.0 and HSA. So this is execution time, so lower is better. So here you see that HSA actually got a huge improvement in performance versus directly compiling to the ISA. Okay, and in AES, it didn't always win, but it was quite a bit better. So the original value proposition was basically, we'll abstract out the programming complexity of all of these processors, and we will not cost you a performance penalty. And so here, in a pre-HSA 1.0 device, but with most of the features in it, we got very, very good performance. Now, we didn't always win, and there are other benchmarks where we are not as good. So I do invite you to go look at this. We believe that that's because it was a pre-HSA 1.0 device, which had some throughput limitations. And when the newer devices are rerun, we expect that the same kind of general benefit will occur. But primarily, most of this comes from not having to copy anything and having user-level communications between all of these different programs. So CodePlay from Scotland also did some analysis with C++ on HSA. So the previous one was OpenCL, this one's C++. So from financial world here, they did options pricing, and so HSA did as well, or better, or approximately equal to OpenCL, and it had a slightly smoother performance curve characteristic. So OpenCL had kind of inconsistent performance at some sizes of arrays, and this one was a little bit smoother. But in general, achieving its goal of being equivalent on par with direct to ISA compilation with no performance penalty. So here's an example from AMD of translating CUDA code to HSAL and then executing HSAL, and they show that they got full utilization and full streaming of the graphics card in the HSA system, in this case without any manual intervention. Another interesting thing, so normally you think about virtualizing CPUs, like running VirtualBox on them and getting certain performance guarantees on the CPU side of things. A university from National Taiwan University and some others, Tsinghua and others in Taiwan, decided to do the same thing with a GPU. So they virtualized the GPU to allow multiple HSA systems to be running on it, gave it some performance and resource allocations, and they were able to find that they achieved, in most cases, 95% of the native performance, but now with your GPU virtualized and executing these HSAL programs. Okay, so preliminary, more results coming, but so far it seems you can put together this whole system, have no performance degradation, and in many cases you're getting a performance improvement because you've removed a lot of the operating system overhead and now are doing things at user level, and you can do that specifically because of the APIs that we put together. So let's talk about products. So very recently, Carrizo has been introduced from AMD. This is a fully HSA enabled chip. It's available now from Asus and Dell and others, Lenovo. It includes this IOMMU, which allows the GPU then to participate in the same cache coherent shared virtual memory as the CPU. ARM has been a founder since the HSA Foundation launched. They have publicly announced they're building these heterogeneous systems already. They've included the full memory coherency and shared virtual memory, and it's consistent with all of the HSA standards. MediaTek also has a roadmap for full HSA support with any number of accelerators and GPUs. They've already started to do some of this integration now, and as they continue, they'll continue to integrate more and more. Imagination has announced that they're rolling out HSA across all their MIPS I-class and P-class CPUs and across all their PowerVR GPUs. And in addition, they'll have a fully compliant fabric that allows all of these HSA compliant kernels and devices to be able to interact across that, along with customer IP. So that will be integrated in their Smart Vision IP platform. Okay, so we talked about hardware, software, developer programming, and systems that are available. So it's just sort of a good time to summarize and conclude how all of this ties together. So HSA Foundation makes heterogeneous programming much easier by providing a single source programming. So your kernel code and your host code are written in the same language, in the same modules, with the same tool chain, dramatically simplifying your programming experience, debugging and things like that, profiling included. You get to choose your programming language and keep your favorite programming language. There's no new programming language to learn. Compilers are provided for many of these and many more coming that will automatically convert that code into HSAL. Much of the performance is improved by eliminating copying data around between host and device. We do that with coherent shared virtual memory, which provides a common address space such that a pointer is a pointer. It doesn't matter what device it's executing on. There is an architected way of sending HSAL programs to any agent. It's set up by the host CPU, and then everyone, including the host, knows how to put and dispatch programs into that. Eliminating all of those operating system calls and all of that layers to get to any kind of device is the primary purpose of the specifications, and it makes it a very efficient runtime. So now with HSAL, there's no longer a need to worry about what's the specific processor that you're targeting. Everyone executes HSAL, and we've shown that there is not a performance penalty for doing so. Finally, we provide everything as open source or open specifications, royalty-free, IP unencumbered. You can get this from the website, from the GitHub, HSA Foundation GitHub. You can download it, you can run it. Right now, all available, completely open source. Compilers, runtime, implementations, everything there to get up and started on an HSA system. So basically, for the first couple of years, we worried about how do you make the hardware platform. And that ended up being cache coherent shared virtual memory. The next couple of years were about how do you build the infrastructure for developers to take advantage of that. That culminated in the release of the 1.0 specifications in March of 2015. Now, recently, hardware platforms are arriving that allow anyone to go and use this, measure it, experiment with it, do research on it. AMD is first out with Carrizo, but others are following. So far, excellent performance results, and there's been no performance penalty or no significant performance penalty for an HSA abstraction, meaning you no longer worry about the exact CPU, DSP, FPGA, GPU, instruction set architecture. Everyone executes HSAL. Just as a hint of what's coming, many of the things of a system are specified for a single vendor to implement. Integrating IP from different vendors is a difficult problem to solve. So you have one vendor with a CPU, a different vendor providing a GPU. How do those separate pieces of IP interact with each other, get access to various aspects of the underlying hardware, the shared virtual memory page tables, and things like this. So that's on the horizon. The 1.1 specifications will be announced very soon, and you'll see some implementation and solutions for now incorporating arbitrary IP blocks from different vendors and still maintaining the same level of abstraction. So thank you very much for your time and attention. You can check us out at the HSA Foundation's website, and you can see at our GitHub the open source implementation of many of these. Please feel free to contact us, and thank you.